Acetic acid, chew. It's a weak acid, and this is a reversible reaction because of that. Because if you remember, when it's a weak acid, the reaction is reversible. So the hydronium is actually a stronger acid than the acetic, which means that the hydronium is going to continue to donate protons back to the acetic acid. So the equilibrium is going to end up favoring, you're going to have more acetic acid molecules than you're going to have hydronium ions. So you'll have a higher number of these than these. Whichever one is the stronger acid is going to push equilibrium the other direction. Okay? Let's think back to our liquid plus heat yields what? Vapor. And if we think about it in those terms, this is an equilibrium thing. Equilibrium is going to end up someplace where we're going to have more particles that are in the liquid phase or more particles that are in the vapor phase. With a reaction like this, it's the same kind of thing. Equilibrium is going to end up somewhere settled where we'll either have more molecules of acetic acid or we'll have more hydronium ions. Because acetic acid is a weak acid, it's not really good at getting rid of its proton. It's like a lousy gift giver. So it's going to tend to take that proton back because it just doesn't have the strength to push the proton away from it. So we're going to end up with equilibrium being over here on this side. Equilibrium always ends up on the side of the weak acid. So the equilibrium is going to end up on the side of the weak acid. You can think about it in terms of the strong acid wins. The strong acid is really good at pushing its proton away. The stronger acid will win. Your life, have you seen or heard the prefix amph? A-M-P. Well, A-M-P-H, amph, not amp, not like an amplifier, but amph. Amph. You all have. You just don't know it yet. Bingo.
I'm not sure how you got that out of that. Is that a lizard?
No, it's a frog. It's just a really bad frog, and that's a tadpole. Yeah, it's pretty terrible. But yeah, amphibians. So, what's so special about amphibians? They change forms. They're aquatic in part of their life, and they're terrestrial in another part. Amphoteric compounds change. Amphoteric compounds can be acids or bases. Water is the classic example. Depending on who it's hanging out with, water can behave as an acid or water can behave as a base. It's one of those. It all depends on who it's around. Now, the hydroxide ion, our old friend, OH1-. This is a pretty important group. If you go on to a college chemistry class and you take any organic chemistry, you will learn to call this a hydroxyl group. Okay, it is called a hydroxyl group. When we add it to an organic molecule, we say, oh yeah, we put a hydroxyl group on that. So for instance, we can take methane, we can add a hydroxyl group, and we get methanol. Okay? And methanol is an alcohol. It's methyl alcohol. So we can take ethane, add a hydroxyl group, we get ethanol. That's ethyl alcohol. So OH groups produce compounds known as alcohols. Now, not all of those are the kinds of alcohols that people consume. They're like methyl alcohol will kill you. Propyl alcohol will kill you. Do you know what propyl alcohol is? Rubbing alcohol. Isopropyl alcohol. Isopropyl alcohol is rubbing alcohol. When we have any compound that's got a hydroxyl group, some compounds with hydroxyl groups are acidic, some are amphoteric. So, because it's such a broad array of things that can have a hydroxyl group, they can either behave as acids or they can be amphoteric and go both ways. If the compound is going to be acidic, this hydroxyl group has to be able to shed its proton. It's got to be able to shed its hydrogen. So, and it's got to be able to donate it to water. That would not happen with methanol. That would not happen with ethanol or propanol. But there are compounds for which it happens.